you're going to have trouble with these. Now, just plug them in. If you can, use the E over the LN. Because when you do this, it automatically does this. If you're on the 83, it automatically gives you the caret and the parentheses. This one, not a problem. You're going to put it in without the parentheses. This guy down here, you have to be careful. Now remember, that exponent only belongs to the E, not to the 50. So when you do this, 50 times E raised to the 4x, or whatever we're putting in there, 4 times 0.02. And you don't put any parentheses in there. It's saying take E, raise it to 4. Then multiply it by 50, multiply it by 0.02. So you only want that in your exponent. So make sure that your exponent has parentheses around it. Now, if you use the E on the other side of the calculator by the clear word, you have to physically put the parentheses in there. You have to put the parentheses in there. So this was a good exercise in making sure you can put it in your calculator. A lot of times kids will say, but I didn't get that answer. So I have to say, okay, let me see you put it in your calculator. And I'll say, well, I don't have it. I put it in last night. I don't know what I did. So if you're not sure, make sure you use the parentheses, and then we can see where you're going from there. This one, I just threw a graph at you, and it's probably difficult to see because it's riding very, very close to the axis. So what you want to do is you want to maybe make your window, keep your x's, keep your y's from like -1 to +1, so that you can see a lot closer what it's doing, because your calculator can't get any more exact. Oh, is that your water bottle over there?
No, wait, yeah.
It was under your desk yesterday. Okay, so now, this should say relative max. This is a relative min. That's a relative max. And just, to keep you graphing and looking at your max and your mins. Realizing that some of these give us a little bit of a different look to it too. Okay. These were important, and probably my fault. I didn't give the best directions to it. We ended quickly. I might not have been able to express what I wanted you to do. For both of these problems, you use the same investment, $2,500. And what the goal was to use that table for both. I probably should put the table in both sections rather than at the top. So I'm going to make that change. But what you're doing here is you're changing your n. How often you compound this. So what it's asking you to do is take these pieces, put this in. See if I can focus this on this. You're changing your n. How many times do you compound this information? We started with yearly. Then we went to semi, twice a year. Then we went to quarterly. Then we went to monthly. Then we did daily. And then last we did continuously, per. To see same investment, same interest, which is giving you a better return. Now, granted, there's not a lot of difference from the beginning, the lowest to the highest. There's not a lot, but per gives you the best one, the continuous one. The 365 is real close to it. As you invest a larger amount of money, it's going to be a little bit more obvious. When we came to this one, same process, I just increased the rate and I increased the years. If you increase how long you invest something, you obviously are going to make much more, right? Even if you put $10 away now, made $1 a year, it's going to return you much more if you left it in there for 100 years rather than 2 years, right? So again, your compounding keeps changing. I missed it on this side. Quarterly, 360, monthly, I'll move that over in a second. Again, continuously is going to give you your best return. money will give you your best return. And if you take a look at your front to your back, your smallest to your lowest, you do have more of an increase because number one, your interest rate was higher and you left it there for more years. So you do have a bigger difference than just leaving it in there for 10 years at 2%. So this is what I was hoping that you would see. The next part of it was also consistent. It took do everything continuously and just change the amount of years you left this in. You're investing $12,000 continuously across the board, but you're changing how many years this is in. You're changing your time. So each time we said 1 year, 10 years, 20 years, 30 years, 40 years, 50 years. Per is nice. There's no fraction involved. So you should be able to tell the difference between leaving it in there 1 year versus leaving it in there 50 years. How much money you will make. And then the other one, the percent and the top one went a little higher, so this percent went a little lower. So you should see the difference between a smaller percent. You're still making a lot more money, but at a little bit of a slower pace. The goal is to keep the amount that you invest consistent and something else consistent. Either the rate, the time, and just change the compounding, or change the time and keep the rate the same. So you want to just change one thing at a time to see what is that doing for you. That's what I was kind of hoping you would get. Not to be redundant to make you do this 6 times, but so that you would actually kind of get a peek at what's happening over time. You know, changing your years is the biggest thing. Questions? Good? All right. Today, we're going to work on your basic increasing, decreasing exponential functions. We're going to take your exponential functions and we're going to align them to something in real life. And they lend themselves to science like half-lives and double lives and things like that, half-lives. They lend themselves to half-lives, bacteria. I was telling my first period, when something grows exponentially, it keeps feeding upon itself and growing and growing. Like, say I took this class and I cloned everybody. I made a clone of you. So say there's 15 people. Say there's 20 people. Let's make it easy. Now we have 40 people, right? Now each one of those 40 people are going to clone. So we get 40 more people. 80. And each one of those 80 are going to clone. We're not just increasing by 20 each time. We're growing exponentially. When something grows exponentially, it starts out a little bit slow because the numbers are small. But as the numbers start to get big, look at the difference between doubling 80 versus doubling 20, right? It's a bigger difference. When something decreases, it decreases rapidly and then starts to slow down. But these are your half-lives. So say you had 10 grams of an element, and it has a half-life. It reduces to 5, big jump. Then reduces to 2.5. Then reduces to 1.25. You see it kind of slow down a little bit? It will never get to 0, and that's why your exponential curve rides along the x-axis.
Wait, so are we gonna have asymptotes then? Like 0 to 80?
That is your asymptote. Your x-axis is your asymptote. Your x-axis will be your asymptote. It falls into your regular exponential curves. We basically, and I gave you this, but I want you to write on this with me. This is your basic formula for growth and decay. Now, I just want to show you something. You don't have to write this, but this is what we were using for your interest without any compounding, because we don't compound with bacteria. This is what we were using before, right? So it is essentially this, A, B to the X, as an X, or time. It essentially falls into this. This is where your rate goes. This is what your initial value is. There's your exponent, time. Okay, so we're going to use this AB to the x as our basic formula. That's all you have to memorize. If something doubles, A is your initial amount, B is your rate of change, and X is time. So if something doubles, what is my rate? What is B equal to? If it doubles, how do I represent doubling? Square or 2, right? If I triple, what am I multiplying it by? 3. If I half, 1/2. So this is how your rate's going to go. If I decrease by 2%, my rate can't say divide by 2, it's decreasing, it's subtracting 2, so I'm going to be 1 minus 0.02 is my B. See the difference? If I increase my population by 5%, what's it going to be? 1 plus 0.05. Isn't that what we do with our compounding money too? We 1 plus it to keep adding to it. We 1 minus it to decrease it, to depreciate it. So those are the things we're going to look at. Now the only other thing we might have to do is worry about your exponent. Your exponent is time, but sometimes we have a pattern for time. It doesn't happen every day. It happens every 2 days, every 10 days, every 12 days. So we have a cycle that it has to go through. And we take the time and say it happens every 4 days, we divide it by 4. And we're going to take a look at this. And what I want you to do is get a good feel for these. So let's take a look at this example. And before we even put it in a formula, we're going to figure out what it should be. I have a number of the bacteria that triples every 4 days. And initially, I have 1,000 units. I want to know how many units of bacteria will be present after 4 days, after 8 days, after 12 days. So let's think it out without a formula. Initially, I have 1,000 units. It's going to triple in 4 days. So at 4 days, what should I have? 3,000. Every 4 days. So when else is it going to, when's the next time it will triple? 8 days. How many will I have? Good. This is times 3, 9,000. When's the next time I will triple? 12. How many will I have? 27,000. So you kind of see this pattern here? Right? Because it's tripling every 4 days, not every day.
That's just the chart.
That's just a chart. That's how we got that one, right?
That's that.
Well, that's coming off when we graph this. I took that from when we graphed it. But this is what we do, what we figure out, right? Now, let's set up our equation. How many units of bacteria do you start with? 1,000. What's my rate that it's changing? What's it do? Tripling, 3, every 4 days. So X, not every day, X represents days, but X over 4. Every 4th day, I want to do that formula. Every 4th day.
So that's an X.
X over 4. Now, we're going to put this in your calculator. You got to think about your window for a minute. You got to think about your window. What quadrant does this take place in? First, I can't have negative time. I can't have negative units of bacteria. So automatically, your X min and your Y min are at 0. Your X represents what? Days. So X max, what should I make my X max be? I really want to do up to 4 days, 8 days, 9 days, 1 day. What's the maximum I want to look at? 12. So I'll make this say 15. Just so I get off my graph a little bit. My Y max. My Y represents how many bacteria are going to be present. Now in 12 days, how many do I have according to my chart? 27,000. So maybe I'll just make this be 30,000. Okay? And graph it. See if your table looks like what we thought it should be. Because if your formula's off, it won't look like that. So you see a decreasing value. You see an increasing value. It doesn't start at the 0, it starts at 1,000. Right? So it goes like this. Now the trick is, sometimes you don't see it sharp enough. So maybe you want to expand the X a little bit. Make the X a little bit longer. You'll see it grow sharper. It depends how many days you're looking at. We only needed 12 days. But over time, this is going to shoot up. 1,000, then it's 27,000, then that's got to triple. 81,000, that's got to triple. So it's starting to pick up as it grows. So if you increase your X's, you make that longer. What it does is it just makes this sharper. Okay? And this is the rest of your table. We knew this one, we knew this one, and we knew 8. We knew that one. Right? So we're going to stick with this format and work off of that. Okay. Questions? Not bad, right? Not bad. Okay. So now, I have a town whose initial population is 100,000 people, and the population is decreasing. It's a sad town. People keep leaving. So, it's what? The population keeps decreasing. You know what? The one city around here that's doing really well and growing is Middletown. Yeah.
I don't like Middletown. I don't like anywhere.
So, the population decreases at 2.5% per year. So we want to know, when will this population reach 95,000? Now, we could do it ourselves. We could take 2.5 off of 1,000, 100,000. Then off of that, we could take another 2.5% off of the one remaining. And we can keep doing this, or we can graph this. Now, we start with A, B to the X. What is A? What did we start with? 100,000. What's our rate? We're decreasing 0.25. So how do I have to write this? 1 minus, and how do I say 0.025?
It means it's 100,000?
100,000. Right? It's 100,000. Now, my exponent is time, and time is in years. So, X is my time. We're going to put this in, your Y equals. But we're going to have to change your window. Without looking at your table, let's think about your window for a second. Again, X-min and Y-min are at 0. My Y before we put the second part in, we just want to get this one straight. My Y represents my amount of people, and my amount of people is decreasing. So what would my Y max be good at? 100,000, because I'm decreasing, right? Or 110,000, whatever you want to start it at. Now my X represents my years that this is going to happen. I don't know, let's just make it 10. Now, graph this first. So you should get a graph that starts decreasing. Except for my little jump in my screen here.
Doesn't even like go
There's no lead.
far to the. It's just kind of.
It's sort of.
It's just kind of.
It starts here. You don't have a lot. So how could you make it be sharper? And that's a good point. This is what I was trying to get you to see. Like Rebecca says, yeah, and it kind of almost looks like a straight line here. How could I get this to dig a little bit deeper here?
Increase the X.
Increase the X. Throw your years up there. Make X be 50. What happens? Make X max be 50. It drops a little bit down further, right? We see it coming down.
It's like half.
Right, because look, this only went 10 years. You're only losing about 2% a year. You're not losing that much. Over 50, isn't it going to come down a little bit further? You'll see it a little bit steeper. That's what I was trying to tell you about the X max. So, but we don't really care because all we care about is when does it hit 95,000. Now, Y2, put in Y2, 95,000. And let's see where they crossed. So, as you do your graph, if this was your graph, 95,000 should be pretty far up to the top, right? Do an intercept. Second calc, number 5, intercept. Enter, enter, enter. We can't solve these algebraically yet because the exponent has the variable. We need logs to do that. But we can certainly solve this graphically.
Okay.
How do you do this?
What?
You're looking at top.
Oh, I was. What was that? 32?
So
Okay.
110.
110. Thank you.
Wait, why does it go first?
Sec, you gotta hit enter 3 times.
Yeah. 2.025.
Yeah, that's it. So you got the X at 2.025?
Yeah.
It'll take a little over 2 years for this to decrease to 95,000. It's not asking to decrease that much each year, and you're only asking from 100,000. You're losing 5,000 people. So you can kind of estimate it. 2.5% is 2,500 people right there.
Could we like also like what is estimating okay or does it have to be like
It will have to be exact.
Okay.
It has to, because your table doesn't show that exact
Yeah.
amount. It doesn't show that exact amount. So you have to set the Y2 and see where they intersect. But the Y2 is nice to set to see where they intersect, right? So remember, if my population was increasing, I would be here. I would be 100,000, 1 plus 0.025. And now my graph would go the other way. I'd be way up here. So your Y max can't be 100,000. That's where it's going to begin. Your Y max is going to have to be like 300,000 because you're increasing. But draw a sketch of your problem and see if you can come up with your windows from that. If not, put it in your calculator, go to your table. Use your table to help you make your window. Okay, and one more. Half-life. So has anybody had chemistry in here? Half-life. What kind of elements usually have half-life? Radioactive materials, carbon elements, anything radioactive, kryptonite. Superman's kryptonite has a half-life. That means it starts not being as effective, right? And it goes in cycles. And does a half-life go every day? Well, yes, it loses every day, but it jumps. It could be 20 years before it hits a half-life, right? Over time, it could be 20 years. It could be days. It could be years. Now, we're going to do our rate this time as a half because it's a half-life. I'm decreasing. I'm making a decreasing exponential function. Stay with me, guys. Come on, one more problem. So I start with my y equals ab to the x. So they told me my half-life, so I'm halving, so I know the b is the half. And let me put this in first. They told me my half-life is every 12 days. What do I do with the 12?
X over 12.
X over
Ah,
12.
that's what I forget.
Good. How quickly they forget, right, Sean? I'm glad you're on the ball today. X over 12, this is your cycle. Every 12 days, you're going to cut it in half. So, we're going to start, we don't have an initial amount. So, our initial amount has to stay A. But I got a problem because I have two variables. So, they give me one more piece of information. There are 4 grams left after 10 days. So days is my time. This is my time. That's my X value. This is what's left. Where does that go? Y. 4A. 1/2. X is 10 over 12. I'm sorry, this is a 12. It's just not coming out. 10 over 12. Now, remember, this exponent only goes to this. I'll write it on this side. This side, maybe that side works a little bit. The middle is just not cooperating. Okay. This exponent only goes to this. These are factors. These are being multiplied. So technically, all I have to do is divide by this mess, and then divide both sides by this. So take 4 divided by 1/2 raised to the 10 over 12. And we'll find out how much we initially started with. What did you get, Ben?
7.127.
Okay, let's see if Ben is right. If we started at 7.127 at the 0, after 12 days, what should I have? What's half of this? Give me half of that. 3 point something. Okay, so 3.563. Now, we have, after 10 days, 4. Ah, that looks right, doesn't it?
Yeah.
Yeah, so we're decreasing down to its half-life. It's a good way to check. A very good way to check. Okay, so when we have a decrease, a half-life, we're going to use our rate. And think this out logically. You need to know what variables you have. You need to know what you're looking at. Questions?